Hello, this is Ralph Baker, Chairman and Chief Scientist of TerraTherm, and welcome to TerraTherm's webinar series. It's 12 noon Eastern Time, and the agenda is that I will give this presentation for the next half hour or so. And during the presentation, you're welcome to use the question box to ask any questions you have. Once we get to the end of the presentation, please click on the hand icon to raise your hand, and I will unmute you so that everyone can hear you ask your question, and I'll answer it. So let's begin. Also, I should mention that at the end there is a survey we'd like you to please fill out to provide us with feedback so we can continue to improve our webinar series. The title, In-Pile Thermal Desorption, IPTD for Treatment of POPs-Contaminated Soil and Sediment, is our topic. The overview is as follows. I will introduce thermal conduction heating and the family of technologies called in-situ thermal desorption and in-pile thermal desorption, or ISTD, IPTD, for treatment of persistent organic pollutants, which I'm going to henceforth refer to as POPs, contaminated soil and sediment. After I introduce the topic, I will launch into two different case studies, the first being one about a Ministry of Environment of Japan IPTD demonstration that we carried out with a partner, and a current project that we're doing for the U.S. Agency for International Development at Da Nang Airport in Vietnam. I will also discuss some other ways to implement IPTD and close with some remarks about the sustainability of the process. When treating organic contaminated soil and sediments, one of the most important physical properties of the contaminants is their vapor pressure curve as a function of temperature. The VOCs that are shown on the left-hand side of the family of curves are typically treated at around the boiling point of water. But in treating POPs, such as PCBs, dioxins, and organochlorine pesticides, it's necessary to get to much higher temperatures to get them to behave as if they're VOCs and have enough vapor pressure so that they can be evaporated from the soil, desorbed, and then treated. We've found for dioxins that a target temperature of 335 C is appropriate. And note that mercury, a metal, can also be treated around the same target temperature of 300 degrees C or so. Thermal conduction heating is the method that we use for treating these higher boiling constituents. TerraTherm also offers two other widely used techniques for in-situ heating, namely steam-enhanced extraction and electrical resistance heating. But neither of those techniques can heat the soil to above the boiling point of water, whereas thermal conductive heating can be used both for lower boiling constituents and these high boilers. TCH involves placing steel pipes into the soil to be heated, and inside each steel pipe, as you can see on the left, is an electric heating element. It therefore conducts electricity only within the heating element, not through the soil, and delivers the same wattage of heat throughout its entire length. The pipe is non-perforated pipe, about 3 inches in diameter, so it's easy to install in the soil, and then when the heater is fully turned on, it's much like the heater on an electric stovetop. It can be turned up or down. It operates at around 600 to 700 degrees Celsius. So the heat moves out from this hot pipe into the surrounding soil by thermal conduction, basically by grain-to-grain contact of the heat. The diagram on the right shows both the arrangement of two heaters with the soil in between and the progression of heating between those heaters. Initially, when the heat is turned on, it's very hot at the heaters and at ambient temperature in between them. But soon we rise up to the boiling point of water right here, and we sit there until the water boils off, during which time there's quite a bit of steam stripping of the volatile organics. And then after we drive off the steam, we're able to get up to higher temperatures than the boiling point of water until we reach the boiling, the target temperature, in this case 335 C for dioxins, in the coolest locations in between the heaters. So this process of heating by thermal conduction results in very uniform heating of the target treatment zone, and the array of heaters is designed to achieve that target temperature within a practical period of time, which is often about 4 to 6 months. Initially, when Shell Oil Company invented the IPTD process, they also envisioned the ex situ counterpart, which we've called in-pile thermal desorption, or IPTD. And here's actually a photograph of an early Shell project done in the late 90s to treat PCBs on the island of Saipan in the Western Pacific for the U.S. Army Corps of Engineers. The pile is visible in the foreground, and this was done somewhat differently than we now do it, but it was an early application of IPTD for treating PCBs, and earned an award from the U.S. Army Corps of Engineers for innovation at the time. Since then, this process has been used at a number of POPs-contaminated sites, and these 4 are dioxin-contaminated soil projects. A Superfund site in Missouri, a Navy site in California, a project that we did for Southern California Edison treating creosote-contaminated soils, but also dioxin, and a project that we'll talk about in a moment for the Ministry of Environment in Japan. The volumes treated varied, as you can see in the first column. The pretreatment concentrations, though, across the board were high in terms of picograms of 2378 tetrachlorodibenzodioxin equivalents, or TEQ, per gram. Post-treatment, though, the post-treatment concentrations in the soil are very low, and in fact much lower than the 1,000 picograms per gram target that applied to these projects. And the exhaust gases were monitored by independent third-party source tests and produced very low results in terms of nanograms per cubic meter compared to the standard of 0.2 nanograms per cubic meter that applied to the U.S. projects. Each of these projects is well documented, and the last slide will provide the references. So the first case study is the IPTD demonstration that we performed with our partner in Japan, Shigatech, on dioxin-contaminated soil in a small demonstration scale box. This project was highly scrutinized by the Japanese government and academia, and involved placing 1 cubic meter of heavily dioxin-contaminated soil in a box that was insulated on the bottom, sidewalls, and top, into which were installed heater wells and vacuum wells, with the resulting off-gas going into a thermal oxidizer, heat exchanger, activated carbon vessels. These are the blowers, and the stack. So the soil was heated by thermal conduction, as I described before, moving out from each of these heaters, and the heaters operated at a temperature of around 700 C. So the soil temperature close to the heaters was in the 500 to 700 degree range, but the target in between at this particular site was 325 C. So this is what it looked like. It was all done within a sprung structure. with a portion of the building devoted to the treatment tank, which you can see in the bottom center photograph. There are the wellheads above each of the heater wells, and the off gas coming out to the foreground. That was conveyed then into the room where the treatment equipment was. As I mentioned, a flameless thermal oxidizer, heat exchanger, activated carbon beds, and the stack. And those can be seen. Here's the thermal oxidizer in the upper left, the heat exchanger, the carbon vessels, the blowers, and the stack going up through the ceiling of this building. Now, while there's a great deal more evaluation and monitoring that was done than I have time to report on here, I will focus on a few things that I think are of greatest interest. One is what happened in the treated soil itself. The second is the measurements that were made of the off-gas evolved from the heated soil ahead of the treatment system. It's unusual to have this kind of information, but it was collected in this case. Then we have the treatment train and the off-gas as it was prior to being exhausted to the environment. Also, and rather unusually, the ambient air was measured around the property, and I will talk about that next. But there were also a lot of other things measured in this demonstration scale project. So here's a site plan showing the property, which was located in Shimonoseki, which is part of Yamaguchi Prefecture in the western part of Honshu. Here's the treatment building, and there were 4 locations around the perimeter of the property, shown A, B, C, and D, where the ambient air was measured, the dioxin in ambient air, before the demonstration, during the demonstration, and afterwards. You can see that while the concentrations did go up 2 to 3 times during the demonstration, at highest they were well below the environmental standard of 0.6 picograms per cubic meter for ambient air. And then they dropped down to concentrations after the demonstration very similar to those before. So this is very interesting from the standpoint of what potential exposure might be represented in terms of neighbors of a site. Now for what happened in the heated soil. There were 1,800 picograms of TEQ per gram pre-treatment and only 68 post-treatment, which was well below the Japanese standard of 1,000 picograms of TEQ per gram that we were shooting for. So, so far so good, and there were no changes in soil characteristics observed. This is not like heating the soil hot enough to cause it to fuse together into a brick or anything like that. Most interestingly, we are able to show you the progression of soil temperatures over the month-long demonstration, as well as the off-gas that occurred from the heated box. So first, for the soil temperatures, the blue curve shows the lowest temperatures measured in the box, the green, the average temperature, and the red, the highest temperature. And again, it varies because the highest temperatures are closer to the heaters and the lowest temperatures are in between the heaters. It's evident that the lowest temperature locations did get up to the target temperature of 325, while the highest temperatures close to the heaters were close to 600 C. The peak concentrations evolved from the box, but ahead of the air quality control system are shown by this curve. We can see the concentrations began to go up at the time that the hottest locations first broke above around this 300 C temperature. So up until that point, the dioxins, which are very recalcitrant, remained sorbed to the soil. but once you get up to above 300 C, someplace in the box, we start to generate a small amount of dioxin in the gas evolved from the tank, and that's what's evident in this peak. Went up to about 0.46 nanograms of TEQ per cubic meter before dropping back down to very low concentrations. But most importantly, in terms of what was discharged after the air quality control system, it was at highest 0.00018 nanograms per cubic meter compared to the standard of 0.0006. So we stayed well below the standard throughout the project. And based on these results, IPTD was approved by the Japanese government for treatment of dioxin-contaminated soil or sediment. Now on to a current project that we're doing in Da Nang, Vietnam. Our client is the U.S. Agency for International Development, which is the agency that's been charged with addressing this hotspot where dioxins are present in soil and sediment due to the use of Agent Orange herbicides, 2,4-D and 2,4,5-T, during the Vietnam War by the U.S. military for defoliation of the jungle. And at this location, which was one of our air bases, there was a large amount of the Agent Orange chemicals stored, mixed, and loaded onto aircraft, and to the degree that a fair amount of highly contaminated soil was delineated at the site. Approximately 190,000 square meters, which is about 40 acres, and a total of almost 80,000 cubic meters, or about 105,000 cubic yards in this area marked in yellow. USAID and their subcontractors performed an environmental evaluation to decide what to do at the site. They considered landfilling on the airport property, both with and without biological enhancement, and using ISTD/IPTD. The problem with the landfilling, other than it of course doesn't actually carry out treatment to very much of a degree, is that it also had higher environmental impacts than using IPTD, which had the lowest environmental impacts and a cost comparable to the landfilling. So it was decided to select IPTD as being the most implementable, proven technique that could meet the goals at the site. This was in part based on treatability testing that was done on the soil and sediment from the site. So we've done several rounds of it, but these data are representative. We went from very high concentrations in the soil, over 100,000 parts per trillion, down to below the 150 part per trillion goal after 21 days at target temperature. So this is the residence time at target temperature. And for those of you who may be more familiar with incineration of soil and wondering why a temperature of 335 C could be sufficient, it's really this long residence time at temperature that makes the difference. With incineration, it's typical that a packet of soil is only heated to the target temperature for seconds or at most maybe a minute. And here we're able to heat and stay at temperature for days or weeks. This 3D simulation is put together by USAID to help you understand what we're doing at the site.
The environmental remediation at Da Nang Airport project in Da Nang, Vietnam utilizes a remediation technology called in-pile thermal desorption, or IPTD. IPTD is a proven technology capable of destroying dioxin and has been used successfully in the U.S. and Japan. The technology begins with the construction of an insulated above-ground containment structure. The structure at Da Nang is about the size of an American football field and is capable of storing approximately 45,000 cubic meters of contaminated soil. The walls of the structure are built with prefabricated concrete blocks to a height of about 8 meters. A heavy plastic liner placed at the bottom of the pile prevents liquid from escaping. The liner is then covered with various layers of crushed stone, sand, and insulating concrete. Drainage pipes are placed at the base of the containment structure to capture contaminated liquids, otherwise known as leachate. Once the structure is complete, dioxin-contaminated soils and sediments are excavated from the Da Nang Airport site as determined through the environmental assessment conducted by the United States Agency for International Development, or USAID, in 2010. The environmental assessment characterized the extent of dioxin contamination at the airport and served as the basis for remedial design. Due to the volume of contaminated soil, approximately 73,000 cubic meters, remediation will occur in 2 phases of excavation and treatment. The first phase largely involves excavating and treating soils from the southern half of the site and will conclude in 2014. The second phase, scheduled to conclude in 2016, largely involves excavating and treating sediments from the northern half of the site. After the structure is filled with soil and sediment, it is covered with a layer of gravel and an insulating concrete cap. Approximately 1,250 heater wells are then inserted into the pile. The heater elements inside these wells are critical to the remedial technology and are responsible for heating the contaminated soil and sediment. A horizontal vacuum extraction system, which maintains negative pressure, and air injection wells, which ensure adequate oxygen supply, are also installed. Here is another view of the different layers of the containment structure foundation and sidewalls. The plastic bottom liner, perforated pipes, and layers of crushed stone, sand, and insulating concrete make up the foundation and drainage system of the structure. Metal sheet piles and lightweight concrete walls placed between the blocks and the contaminated soil help insulate the soil and minimize heat losses. As liquid drains from the contaminated soil and sediment in the pile, it is collected by leachate pipes at the bottom of the containment structure and conveyed to the north end of the pile. Air inlet wells supply oxygen to the pile to improve dioxin destruction. Heater wells raise the temperature of the soil and sediment, and the horizontal vacuum extraction pipes collect steam and vapors released from the soil and sediment during heating. All liquid and vapor waste is transported to a treatment plant constructed north of the containment structure. The IPTD system is powered by 2 electrical substations on either side of the containment structure, built by USAID's Vietnamese project partner, the Ministry of National Defense. Once the IPTD system is started during each treatment phase, it will gradually heat the soil and sediment to a target treatment temperature of 335 degrees Celsius or 635 degrees Fahrenheit. This will take approximately 4 months for Phase 1 and 6 months for Phase 2. The prolonged exposure to high temperatures causes the dioxin compounds in the soil and sediment to break down into non-hazardous byproducts such as water and carbon dioxide. Based on treatability studies and previous applications, approximately 95% of dioxin trapped in the soil and sediment at the Da Nang Airport is expected to be destroyed in the pile. The remaining dioxin will be collected as liquid and vapor waste and treated and tested in the respective water and vapor treatment systems before being released into the environment as clean water and clean air stream.
So the U.S. Agency for International Development awarded TerraTherm a $37 million contract in 2012 to install the system that we had designed and operate it. This photograph shows the treatment structure, the pile structure, as it was when it was being installed by another contractor. And then when turned over to us, this is our installation of the heaters. As I mentioned, in only 18 days installing over 1,250 heaters. This is what the pile structure looks like from the ground. It's 70 meters wide, 130 meters long, and 6 meters high. Internal, that is the soil dimensions, it's actually more like 8 meters high from the outside if you include the bottom and the top. So it's quite a tall structure. But from the top, walking around on it, you wouldn't necessarily know that you were sitting on top of a pile. You might think that this was simply an ISTD project because it looks identical to an ISTD project that would be used for treating similarly high boiling constituents such as POPs. In this case, the thermal wells are 2.7 meters apart, or about 8.8 feet. That's much closer than we use for treating chlorinated VOCs, more typically 15 feet or so apart. You can also see the lightweight concrete insulation layer, which is 2 feet thick, provides a great deal of insulation, and the manifold system for collecting the vapors. And the treatment plant, as I described, looking at it from the top of the pile structure. So currently, this is what the system looks like. We're in operation. We are heating the pile, and in fact, we've achieved and gone past the boiling point of water pretty much everywhere in the pile, and expect to be completed with this phase in November. That will be followed by confirmatory sampling, quenching the hot soil by adding water, and then emptying it and refilling it with a second phase to be done in 2016. I'd also like to introduce a different approach for treating smaller volumes. Obviously, the Da Nang project is very large, but there's many sites with between, say, 2,000 and 10,000 tons of POPs-contaminated soil that could be more cost-effectively treated in a series of chambers, as shown here. In this case, the heaters, rather than being in the soil, are in the walls of the chambers and the floor of the chambers, so that you can fill and empty each of these chambers unimpeded by infrastructure, and we can operate that way in a sequential fashion, with certain of the boxes being filled and emptied while others are under operation. And that's depicted here with, let's say, a system of 8 chambers, 4 of them operating in this fashion, approximately a month to fill and heat, and then another month to sample, cool, and empty, and then the other 4 are staggered. So by doing this, we can deploy a smaller treatment system for treating a certain amount of material, and do so with maximum utilization of the labor force and the treatment equipment, and also with a smaller energy requirement at any one time. And a typical project like this might operate for 12 to 16 months at a site. And it's a mobile system that can be then moved to another site. So I'd invite you to consider the potential for using these techniques. But lastly, I'd like to discuss a little bit more the sustainability of this approach. Because we're treating on-site rather than off-site, we eliminate the transportation to an off-site treatment facility or to a landfill. And that, of course, bears a lot of impacts to the neighborhood: truck traffic, dust, and exposure of neighbors, and saves fuel and resources at the same time. And by treating rather than simply containing, we're eliminating long-term management at the location wherever the soil sediment may be stored and monitored. Finally, compared to kiln-style thermal desorption, this requires much less energy because of the amount of insulation around the heated soil, as I discussed, and the much longer treatment at lower temperatures compared to short treatment at high temperatures. So that brings us to the question phase. We're just about on time, and